Okay, so we're going to define enthalpy as U plus PV. These are all functions of state here, so H is a function of state. And we're going to see now how this is indeed related to the heat flow in and out of a system if you have a constant pressure, reversible work process. So let's take a system under constant pressure, T1, V1, going to a second. This is the system. So let me write the system here. And it's more dramatic if the system is a gas, P, T2, V2. And let's look at what happens to these functions of state, to H, to U, under this transformation. OK, so let's look at delta U. Delta U is Q plus W. That's the first law. And this is a constant pressure path. So now I can write this Q is actually Q under constant pressure. Little p means the path is a constant pressure path. And I'm doing reversible work so that W is minus P dV, where P is the pressure inside the system, minus P delta V. Right? Rearrange that. Delta U is plus P delta V is equal to QP. All right, so this is the heat flowing in or out of the system, and these are all functions of state. Right? This depends on the path. It tells you right here the path is constant pressure. These don't depend on the path. Right? V doesn't care how you get there. U doesn't care how you get there. In this case, P is a constant because the path is constant, so we can bring the P inside. Delta U plus delta PV, it's QP. Take this delta outside again. Delta of U plus PV is equal to QP. And there you have it. There's the H right there, the U plus PV. Delta H is equal to QP. And this is the reason why enthalpy was invented and why it's so important. Because we want to know this. So this is for a finite change. If you want to have an infinitesimally small change, you end up writing dH is dq sub p. It's not always equal to the heat. It's only equal to the heat if your process is constant pressure, reversible work. Okay, so this is the kind of concept that needs to be branded into your brain, so that if I come into your bedroom in the middle of the night and I whisper to you delta H, you should wake up and say QP, right? Heat under constant pressure, reversible work. Should become second nature. This is where the intuition comes from. This is why people write tables and tables of delta H's. Why you have delta H's for all these reactions. Because it's basically the heat. And the heat is something we can measure. We can control. We can figure out how much heat's going in and out of something. This is what we're interested in. OK, so now, last time you looked at the Joule expansion to teach you how to relate derivatives like du dv. du dv under constant temperature, du dt under constant volume. You use the Joule expansion to find these quantities. And these quantities were useful because you could relate then the slope of changes with respect to volume or temperature of the energy with respect to quantities that you understood, that you could measure. And we're going to do the same thing here. So if we take as our natural variables for enthalpy to be temperature and pressure, and we have some sort of change in enthalpy, dH, and it's going to be related to changes in temperature and pressure through the derivatives, dH through the slope of the enthalpy in the t direction, keeping pressure constant, dt, plus the slope of enthalpy in the pressure direction, keeping the temperature constant, dP. And these are knobs that we can turn. We can change the temperature. We can change the pressure. These are physical knobs that are available to us as experimentalists. And so when we turn these knobs on our system, we want to know how the enthalpy is changing for that system, because eventually they will tell us it may be things about how heat is changing further on. Okay? But in order to relate turning these physical knobs to this quantity here, which we don't have a very good feel for, we've got to have a feel for the slopes. If I keep the pressure constant, I change the temperature, what does that mean? What is dH dt? If I keep the temperature constant and just change the pressure, dH is going to change. But how is it going to change? What does this mean in terms of something I can physically understand? So that's the program now for the next few minutes. What are these quantities? What is dH dt as a function? Keeping pressure constant. What is dH dP? Keeping temperature constant. All right, let's start with the first one, dH dt, keeping the pressure constant. And we're going to look at a reversible process. To help us out, but the result is going to be independent of whether or not we have a reversible process or irreversible process. Constant pressure, that means dP is equal to 0. Okay? So for reversible process, constant pressure, what do we know? Okay, this is already branded in your brain, right? Reversible process, constant pressure, dH is dQ. So we can write that down. dH is dQ, constant pressure. That's by definition of enthalpy. That's why we created enthalpy. What else do we know? Well, we can go look up here, looking at the differential. There's no approximations here. This is just inequality. I have a constant pressure process. This term here is equal to 0. That means that dH is also equal to dH dt, constant pressure dt. All right, so now I've got what dH dt is under constant pressure. dH is equal to this, and it's also equal to this. Right? These two are equal to each other. Now, I know how to relate the heat flow to temperature change through the heat capacity. Right? dQ, constant pressure, is the heat capacity. And I have to tell you the path for the heat capacity. So it's C sub P, the heat capacity under a constant pressure path, dt. All right, so these two are equal to each other. So these two are equal to each other as well, which tells me that this derivative, dH dt, constant pressure, is Cp. So now I have my first of my two slopes in terms of something that's related to my system, the heat capacity of the system, something I can measure and I can tabulate. And when I turn my dt knob here, I know what's going to happen to the enthalpy. Okay, so this is the first. This is the easy one. So it's very similar to what we saw with the volume and the energy, where du dv under constant temperature was equal to Cv in this case here. Right. And you're going to find that there's a lot of these analogies between energy and enthalpy. You just change volume to pressure, and basically you're looking at enthalpy under a constant. Anything that's done under constant volume path for energy, there's the same thing happening under constant pressure path for enthalpy.